Hey, thanks for joining me today. I'd like to talk to you a little bit about the software-defined data center. And there are several things we call this. I think one of my favorite is infrastructure as code, because it really starts to make you think about what it is we're talking about when we say software-defined, right? When we talk about the software mindset, we have to think about the whole world as code. For example, think of DNA. DNA is not a human being, but it's sort of a blueprint for a human being, almost a recipe for a human being. In fact, that's another great way to think about software, is we can describe in a recipe book how to take inputs and turn them into dishes, into food we can eat. But we don't need to send you the dish itself to describe it, only the recipe. You add the local inputs, and that software, the recipe plus the inputs, then turns into the dish itself. So if we think about software in that manner, then you think about software defined as the instruction set plus the inputs, and that we can take almost anything and we can start to define it as code. I think Mark Andreessen said it best when he said, software is eating the world. We're turning everything into code. Artwork we've seen recently, AI is painting pictures and things like this. Everything's becoming code. So if we go back and think about software eating everything, what we're thinking about really is we define these as algorithms, and we use these algorithms to quickly adjust the code and instantiate new items, then we're thinking really about business agility. Long ago, we had long development cycles to get software out the door, but today the marketing department thinks of a change in the morning, we write the code, we test it this afternoon, and we have customers using it tonight. So it's much faster once we define it in software, because we can simply have the code implemented and it becomes reality. So no more 3-year refresh cycles, but constant daily, hourly. We hear Netflix can push 1,000 code changes a day into their system because they've software defined their infrastructure. So it's always important to help look back and understand this from historical cycles. So in the mainframe era, we had a large centralized machine, and we had multiple people that could run on this machine at once. But it was very expensive cost per cycle. So in the late 80s, early 90s, we moved to more of a client-server model where we broke that machine up into many servers. And those bare metal servers were each installed, and at the time, we could quickly spin up a new server. It just took a few weeks to spec it, buy it, have it delivered, add an operating system, and load the application on it. But this led to server sprawl, which led to inefficient utilization of each server. So we added a step back towards the mainframe era, where we took the virtualization of the mainframe, we added it to our individual servers, and we entered the virtualization era. So this was great. It also was one of the first steps towards automation on a lot of different things. But even the virtualization era, where you're creating individual machines, individual servers, they have to have the right operating system loaded, they have to be patched, they have a lot of these dependencies, and these are what we end up still calling pets, where we name each server and we give it a name. This pushing it through IT, standardization, update, patching, etc., was actually kind of solved by AWS initially, and now we have Azure and Google and IBM rolling out their clouds as well. But we went to a cloud era where they actually automated these pieces so they could roll out these huge virtualized server farms on their premises, and you could swipe a credit card and it would automatically build a machine. Well, gosh, that was pretty cool. I can swipe swipe my credit card and have AWS build me a VM in minutes, and I can get it up and running. Well, this automation really now is coming back on-prem, and this is becoming what we call the software era. So that era is totally automated, on-prem or in the cloud, or hybrid, more or less, which is where we're going to today. But in order to enable this, we really have to think of this as a software-composed, defined, automated infrastructure to give that line of business agility that we talked about in the last slide, where we think about it this morning and we push it out this afternoon. Give us the developer self-service that they got in the cloud era, but really get to a true automated system that works off of what we call an intent basis. So we're going to go into a little bit more of that intent basis, but why that's so important. Again, I put that last statement up here. A software era is driven by line of business agility and developer self-service is we allow them much more control over packaging up their code and testing it and pushing it out at a much higher speed. To do this, we cannot take the time to create individual servers as pets, as we like to call it. So to do this, we have to be thinking in this software-defined philosophy, right? We need to move from imperative thinking, which is, I command you to use this operating system, and I command you to apply these patches, and I command you to do each one of these individual steps, to a declarative model that says, I want this version of operating system with these patches applied, and letting the software do it in much higher speed, and letting it run through all the commands and spit out a prepackaged, ready-to-go server that then we just put the code on top of, push it out, and it can run. The other thing this allows us to do is when we go from an imperative to a declarative model is when we declare the actual desired state, we can actually use automated processes to go out and look at the actual state, right? The telemetry that tells us the actual state, and provide automation loops to make the actual state as close as possible to the desired state. So we'll see some of this here shortly when we look at some of these software-defined systems. So the other thing that's been happening at the same time as we're moving to this software-defined architecture and software-defined infrastructure and infrastructure as code is actual changes that have occurred in the software development lifecycle. So back in the old days when we had very slow software processes before the cloud age, even under virtualization, we had what we called the waterfall monolithic application methodologies. And these are that we would decide which new features we were going to build into the application. We would spend 30 days building those features, and we'd beta test them, then we'd integrate them all together, and we'd integration test them, and then we'd send them through QA, and we'd have a release cycle. So the interesting thing about this is it really wasn't until QA passed that the developers were actually released to work on the next set of features. So what you had is you had developers who got really good back in the day at Doom and Quake, and now I guess it would be World of Warcraft or World of Tanks or whatever they're playing today. But what we really wanted to do is speed up that beta test cycle and remove some of the integration dependencies, and to be able to do QA test on smaller things and have a much faster release cycle. So what they did is they broke up that waterfall and they turned it into an agile sort of methodology. So what we do is we actually work off of APIs. We break our services up into independent units that can work together, and we publish the API. Now the API is just how to talk between the two services, right? And we can break these services up, put them in their own small independent units, and then just have them make calls to each other. And in that way, we can roll out individual features to our services every 30 days. Again, if you're Netflix, you can roll them out every day or multiple times per day. But even our standard folks are rolling out 30-day or less release cycles in which they actually produce the feature, beta and QA the feature within their individual service platform, or microservice platform as we like to call them, and they talk to each other. So what we do is, as long as we agree to the API version, we can actually release features on an as-needed basis. So if you look at between day 90 and 120, we may release some new API calls. Maybe our service 3 here isn't ready to implement that, so they're still using version 1 calls, but they want to roll out a feature 1.4 because it's needed before they roll their software up to feature 2.0 parity and use API version 2. They can do that. They just have to say which version of the API they're using. What this allows is the individual teams to be pushing new features in much faster. So if you look at all the features on this slide compared to the last slide, you can see that in 120 days, we can release a whole lot more features and actually push these things through. Some of the other things they do is they've moved to Git, which is a common code repository. What this allows them to do is when their code is all into one place, they can merge it together. They can fork it off, work on development on their own laptop. They can merge their code back into the mainline branch. And then when they're ready to push it for testing, they just push a button, merge it back into the mainline branch, and then that changes its flag and says now it's ready for testing. They use CI/CD pipelines. This is continuous integration, continuous deployment. They can automatically build, test it, run it through management approvals, deploy it in their test systems, test it out, run it through its tests again there, and move it into a production-ready setting. So all of this now becomes automated. So they automate the code check-in, they automate the code rebuilding, they automate the code testing. And what they're even doing is using chat rooms, right, for the output of all these. So you can see when the new main line has been produced. You can see that it's passed unit function testing. You can see as it goes through to container build, gets deployed to the dev test site, goes through its test there, gets management approval, and all these just appear in the chat window. So you can be working on something else and seeing if there's any different status changes that say maybe you need to go back and look at fixing a bug, but you don't have to just be sitting around on your hands. You can actually be working on trying to figure out how to make the next feature work. So they've added all these automation tools to the software development platform, and that actually really speeds up and automates what they do because it automatically pushes it into testing. Whereas we used to have, okay, IT, I need you to build me a test server. Now these systems build them automatically. So, you used to build a VM from IT, you had dependencies, you had to make sure that it was the exact same code you were going to run in production, all that kind of stuff. The cloud providers have made this faster via automation, but of course it's expensive. So one of the ways they've done this, where you don't have to rebuild a server every time, is to use something called a container. And the way to think about this is like a shipping container, right? It's standardized moving goods across the ocean by putting everything into a container. That same container can go on a train or go on a truck. You can load it up at your factory. You can move it across the world, and it can be delivered to the end customer. And it's one standard thing that plugs into a train or plugs into a truck or plugs into a boat. So take that same thing, and what we're going to do is build a server container. And that container is a standard, lightweight server that you can just put your code inside of, and you can automate it. We use what we call a manifest, same as you do in a shipping container, and it will automatically build it, put the right dependencies in, load your latest version of code in there, and then automatically deploy it so it can go into test. And if it passes test, automatically deploy it into production. Okay? So based on Linux, it's been around actually for a long time. Very lightweight. In other words, what they do is you load this server definition on top of a pre-running operating system, and it starts up in about 100 milliseconds, right? Super fast to load and run. Super lightweight. We're not loading an operating system on each time like we did in a virtual machine. So you can now load thousands of containers, right? Each one thinks it's on its own machine. It's secured, separated from the other containers, and it's really easy to automate the build of these and automatically deploy these things. Again, if we compare them with virtual machines, what you see on the left there is you have your infrastructure, then you have a hypervisor layer, and then you have individual OSs, right? And so what we want to usually do here is we want to put aside 8 gigs of memory and 20 gigs of hard drive space for each one of these to load a small, simple app on. Well, in a container world, you don't do that. You run on the shared memory of the host OS and on the shared storage of the host OS. Yes, you can set aside certain amounts of memory if you're going to run, say, a database application in a container. You can set aside amounts of CPU and amounts of memory for it, but you really don't have to. For an application that's a small thing, like, say, a web server that's just simply going to call to a database backend, there's very little overhead in the container model. So very super lightweight. Docker is the 800-pound gorilla of the container space. If you hear that, Docker's just sort of defined way to build containers from a standard manifest, right? So now we've got this way to build super fast, lightweight servers, if you will, server containers, and to automatically deploy them in an automated fashion. Okay, so what we've been building up to is everybody's heard of something called Kubernetes. But what the heck is Kubernetes?